In our next example, we have Miss Caldwell, an insurance agent, often telephones persons at random in hopes of arranging appointments to discuss insurance. She's found that 8% of those who are called agree to an appointment, and 30% of those who agree to an appointment actually buy insurance from her. What is the probability that someone called at random will both agree to an appointment and buy insurance? And then it says, use a formula as well as a tree diagram to confirm your answer. So we are trying to find an intersection probability. We're trying to find the probability of an and here. So what we've got is we have the idea of agreeing to an appointment. I'm going to call that the probability of A. The probability that they agree to an appointment is 8% or 0.08. And then the second piece of information that we've got is basically the given. Given that they agreed to an appointment, we know that already, that information, then the probability of them actually buying insurance is 30%. So this would be that they're going to buy it given that they agreed already to the appointment. So this would be like probability of B given that A has already happened is 0.3. And we're asked to find the probability that someone agrees and buys the insurance. So from our formula, we know that this is supposed to be equal to the probability of A times the probability of B given A. So we're supposed to be able to just multiply these two numbers together to get our answer. So let's see, what's 0.08 times 0.3? That is 0.024 or 2.4%. Okay, to illustrate this with a tree diagram, our first branches would be agree or not agree, and I'm going to call that A complement. So that would be my first two branches. Since there's a 8% probability that they agree, I'm going to write 0.08 on that branch. And since the complement would have the other probabilities subtracted from 1 minus 0.08 is 0.92, that would lead to the A complement branch. Now off of the agree, because they have to agree to the appointment before, so the bottom branch is basically dead now. If they don't agree to the appointment, everything stops. But if they do agree, now there are secondary branches that come off of that one, which is that they'll either buy or not buy the insurance. So on that branch, the branch from A leading to B, that's where this 0.3 lies. So we've illustrated this. The first branch leading to A is the probability of A, and that second branch between A and B is the probability of B given A, because you can only get there by going through A first. You have to know that information first. So how this ends up working out is whenever you're following your tree diagram branches, you follow them out and you multiply them. So the probability of A intersect B is what you get from following that full branch out, which would be 0.08 times 0.3, which again is the 0.024 or the 2.4%. So you can kind of see that's how a tree diagram will work along with these. You can write your branches out. Your first branches are your initial probabilities. Your secondary branches are your given probabilities, because the only way to get there is if the first thing has already happened. So that's that additional information. And then multiplying all the way out through your branch gives you the intersections at the end. Let's look at another example here. A firm has 6 accountants, 3 men and 3 women. If 2 of the accountants are randomly selected to attend an accounting seminar, what is the probability that the 2 who are chosen are both men? Find using 2 different methods. Okay, so first let's use the probability formula, and then let's look at a prior method where we've already done problems like this before, and now we have multiple ways we could attack them. So if I look at this with the conditional probability idea, I need to look at what's the probability that the first person chosen is a man. Well, 3 out of the 6 people are men, so this would be a 3 out of 6 or a 1/2 probability. Then I move to my given idea. So what's the probability that the second person is a man, given that the first person chosen was also a man? Okay, so here we have to think a little bit. They've already chosen one person to go out of the 6 people. So now there are only 5 people left to choose from. So my new denominator is a 5. One of the men has been chosen, so one of those 3 men is out of the pool to be chosen, leaving only 2 left to choose from. So the probability that the second person chosen is a man, given that the first person was already a man, is 2/5. Then to find the probability that the first chosen was a man and the second chosen was a man is multiply these two together. So we'll take 1/2 times 2/5 using our formula. So it looks like it's 1/5. Okay, what was a prior method where we had already done this? The prior method is using the idea of combinations. So that's the particular prior method. We could set this up as the fraction of how could we choose 2 men out of choosing any 2 people. So on the top, we could do a combination of, there are 3 men and we want to choose 2 of them. So a combination of 3 choose 2 out of a combination of 6 choose 2, since that's the total amount. If you do 3 choose 2 in your calculator, you should get 3. And 6 choose 2 comes out as 15. So this reduces to 1/5 and we get to the exact same answer. So that should give you some kind of feel good about the idea that yes, this conditional probability formula does work and it does make sense because we've just backed it up with something that we already knew how to do. The conditional probability formula can also be applied to as many events as you may have. So it doesn't have to just be 2 events deep. What about if I wanted to do 3 or 4 or 5 things in a row and I wanted to find this large and probability? We can apply that formula here. So it says a bag contains 10 red marbles and 4 blue marbles. So 14 total marbles. You draw 3 marbles in a row without replacement. What is the probability that all 3 are red? So without writing the entire formula out, we can do this with the conditional idea. So first I'm going to think, what's the probability that the first one is red? Well, out of the 14 total, there are 10 that are red. So for the first draw, there's a 10 out of 14 probability that it's red. Now, given that that has already happened, let's say, yes, a red one was drawn first, so that has already happened. What's the probability that the next one will also be red? We are not replacing them, so now there are only 13 to choose out of, and now there are only 9 red marbles in the bag. Okay, I can go a third level deep here. Given that the first one was red and now the second one was red, I need to do my secondary kind of given probability here. What's the probability that that third one will also be red? Well, now my denominator will be a 12. There's only 12 marbles left. And my numerator will be 8 because only 8 of them are red. Okay, so we can multiply all of these out. It might be easier to do some reducing first, though. So let's see. 10 over 14 is the same thing as 5 over 7. And 9 over 13 doesn't reduce. 8 over 12 is the same thing. If we divide those both by 4, we can get 2 over 3. Then I could even reduce a little bit more. This 3 could become a 1, and this 9 on top could become a 3. And that makes my multiplication at least a little bit easier. So I've got, what, 5 times 3 is 15 times 2, so I have 30 on top. And what is 7 times 13? I don't know that off the top of my head. It's 91, and that's not going to reduce. We could divide it out if we want to. 30 divided by 91. So that's about 3.3% probability of drawing out 3 red marbles in a row. So even though there are more red marbles than blue, it's still fairly unlikely that you're going to draw out 3 of them in a row. Okay, what's the probability you're going to draw 4 marbles in a row now without replacement? What's the probability that they're all 4 blue? Okay, so this is going to work in the same manner, where first we have 14 total, so that'll be my original denominator. The probability of drawing a first blue one out is 4 out of 14. The probability of the second one also being blue, given that the first one was, now there are 13 total marbles for our denominator, and 3 of them are blue remaining. And then this is going to drop 1 every time, so that my third draw is a 2 out of 12. And my last draw is a 1 out of 11. Okay, so we can multiply that out. You can do a little reducing at the beginning if you want to. I'm just going to multiply it. What's 4 times 3 times 2 times 1? That's also 4 factorial. That's 24. And what's 14 times 13 times 12 times 11? That's 24,024. And then let's see, I'm going to just put that in the calculator. What's that? What's 24 divided by 24,024? So very, very tiny probability. Let's turn that into a fraction. 1 out of 1,001. Or a very, very, very tiny probability that that would occur. And that makes sense again because there are only 4. What's the probability that you draw all 4 of the blue marbles out? Very, very, very small probability there.